Okay, welcome back to lecture 2, and we'll just go back to the same slide that we left off on. And remember that I didn't really point this out, but if you look, it says a piece of iron is thrown into copper 2 sulfate. You know to write this reaction because that is the net ionic equation for this. So the sulfate has nothing to do with this. It's sulfate over here, it's sulfate over there. Just ions floating in solution. So it never changed. So I did want to point that out. So here the charges changed on these things. And that's what we're going to point out in this next slide. It says, how do you know what gets oxidized and what gets reduced? I mean, certainly you can predict that calcium is a +2 charge and oxygen is a -2 charge, but getting on top of what the rest of them are, you got to remember your oxidation rules. And one of the first rules is an element in its pure form, in its natural form, and even if it's not its most common form, if it's not combined with any other different element, all of these guys would have an oxidation number of 0. Phosphorus, for instance, is P4. That's just one type of element, so that would be 0. Sulfur can be S8, 0. If it's in its elemental form of any of the allotropes that it can exist in, then it's going to have a charge of 0. If you know that it's a monatomic ion, you're home free because the charge is equal to the oxidation number. They do make a sort of a slight change here. I don't think you'll find a corrector on the AP who's going to be picky about this, but charges are supposed to be 2+. I've been kind of all along telling you guys that that's a +2 charge and a +2 oxidation number. So purists will show the difference between a charge and an oxidation number by writing them different. I'm not a purist on this topic, okay? I'm picky about a lot of stuff, but not that. All right, so oxygen, almost always -2. If you're in a pinch, guess -2 for oxygen. There is one exception. It is quite rare, and by the way, this is not a compound. That's oxidation number, ON, equals -1 in the case of a peroxide ion. You'll know that from the name. This is hydrogen peroxide. Or you'll know that it's forced into it by the fact that hydrogen's always +1 in this instance. So oxygen is kind of being forced into having a -1 charge. As you can see, this has to offset this. It couldn't have a -2 charge because then it would have -2 left over, and that's not the case. So a peroxide is an exception. Hydrogen, 99% of the time is going to be a +1. So you can guess that. The rare instance when it's a -1 is when it's combined with a metal. That is called a hydride, and that's on your yellow sheet. So you can recognize if it's the metal first, followed by the hydrogen. It has to be a metal because something like ammonia, NH3, hydrogen would still be +1. So if it's a metal followed by hydrogen, then it can and will be a -1. So that's an exception. Now, the other ones, you got to kind of go, all right, so boron and fluoride, you go, all right, who wants to be the anion? Who wants to be the cation? Well, fluorine really wants electrons, doesn't it? So it's like, I want to be negative. Let me be negative. And boron's like, okay, I'm cool with that. And chlorine's the same way. It's more negative than this phosphorus, so it will be -1. So understanding those rules and applying oxidation numbers is the very first step in getting this down. Now, something as simple as water, you want to assign oxidation numbers as a single unit. You'd want to say this hydrogen is +1 because hydrogen is always +1 and that oxygen's -2. But if you total these up, they have to equal 0 because there's no charge on the thing. So that's why a lot of times I like to put a little circle around the oxidation number itself so you can be clear about what you're talking about. But you always just do it one element at a time. Something like this, for instance. The chlorine is -1. It's not a peroxide. I'm sorry, it's -2 because it is not a peroxide. There's 3 of them. That gives you a total of -6. And by doing that, you see, hey, there's that little negative charge there. So I have to have one negative left over. So you do a little math, and you say the chloride has to be +5. +5 -6 leaves you with that -1 left over. So something like this, hit the pause, assign oxidation numbers so that it adds up to 0. Hopefully, you figured out chloride has to be -1. It's more electronegative. It wants to have its natural monatomic ion charge, and they sum up to be -5. Therefore, the phosphorus needs to be +5. Now, I expect that you guys can do all this in your head. If you got that one right, don't write any of that down. If this is a little confusing to you, you might want to write down these suggestions at this time. So now we can go back to this equation that we initially said, and we can go, how do I know which one's Leo and which one's Ger? Well, you have to assign the oxidation numbers. And on this one, they write this ON. Certainly, it's okay just in future slides, we're just going to put a number right below there. So oxidation number 0, 0, these are in their elemental form. That's -2. That's the one you would do first because it's kind of a rule. And of course, calcium is going to take on its charge of being a +2 ion. And then you can say calcium goes from 0 to +2. That's up. Jumping lion. What's his name? Leo. Oxidized. Oxygen gets reduced. It's going down from 0 to -2. Reduction in number equals reduction in chemistry. Oxygen gets reduced. Okay? Now, let's see if you're where you need to be. And left to right, assign oxidation numbers to all of these elements. See how you can do. Well, I'm going to take this one compound at a time. Hopefully you tried them all. This one, 2 of them have kind of, rules that'll get you where you need to be. Potassium, family 1, they're going to be +1. Oxygen's going to be -2. It's not a peroxide. Therefore, you use your math to figure out the chlorine. Hopefully this one was a little easier for you. Hydrogen +1, oxygen -2. Remember, that's what it's going to be almost all the time. Hydrogen being +1, oxygen being -2, and then you use your math to figure out that one. You go over here, that's a couple of nice ions. That's a no-brainer. And over here, you're going to use the +1, -2, and you can see the nitrogen with this guy has a little different charge. And that is because nitrogen has varying oxidation numbers. And now we can look at it and we can make this statement. Chlorine goes from +5 down to -1. That's reduction. Nitrogen goes from +3 whoop, up to +5. That's oxidation. All right? So, one of the things we're going to do is talk about these in half reactions as to how this actually happens. How does this go from +5 to -1? Well, it does that by, remember, this is reduction, and it's gaining electrons. And you write that chemically by putting the electrons on the left side of the equation. It gains 6 electrons in order to make that change. The coefficients will come into play when you do this. And that's why we needed the coefficients in the balanced equation, even though the nitrogen only goes from +3 to +5, it's being oxidized, but there are 3 of each one, so each one loses 2 electrons, so 3 times 2, 6. So the total is 6 electrons being lost because there are 3 nitrogens, each losing 2 electrons. So that's an important point, is that those coefficients matter, and therefore the give and take is now equal. We have gained 6 electrons and we have lost 6 electrons. Notice the electrons are written as a product in an oxidation reaction. You should be able to look at this reaction and go, that's oxidation, because you're losing electrons. They're being puked out as a product. Whoop, out come the electrons. Okay? All right. So what is oxidized? What's reduced? Left to right, assign the numbers, answer the question. How'd we do? +2, -2. Okay, use your yellow sheet. 0 there. +2, -2. Start with the oxygen. Lead can kind of be 1 or 2, so your yellow sheet's not going to be as helpful. So that's why you started with sulfur there and oxygen there, because lead is a little bit more flexible. Turns out it doesn't change, even though it's super flexible. But in this particular reaction, it's actually the oxygen goes from 0 to -2, and the sulfur goes from -2 to +4. So you get oxygen going down 0 to -2, colder, -2. That's reduction. Sulfur goes up, jumping lion, oxidation. So I'm hoping that some of you got that one right. One of the things, this will be a great stopping point because it sort of clarifies how these terms oxidation and reduction actually came up. Usually they talked about oxidation as reacting with oxygen. And if you assign oxidation numbers just left to right, hit the pause if you want to test yourself again. Boom, there's +1, -1. You start with the oxygen, and then you fill in for the carbon, and start with the oxygen, fill in for the carbon, and finish that up with water. Now, these oxidation reactions are always going to have oxygen there, and it's always going to be turning into water. That's just the kind of the definition of a combustion reaction or burning. Notice that the oxygen is always going to be reduced, and whatever is burning is always going to be oxidized by oxygen. So let's see if that's the case. -1 +4 up. When you made that carbon, all that nasty carbon dioxide, it went uphill. So that's the change that you see happening. I just saw in chemical engineering news today that they have come up with a process to take the oxygen or carbon dioxide in the atmosphere and turn it into rocket fuel. So I guess we could burn it and then make more CO2, but we can pull it out of the environment anyway. It was kind of a big discovery. So this is the end of the slide here. Oxygen was reduced and carbon is oxidized. Leo and Gur. Okay, so there's your Gur, there's your Leo. Make sure that you get that. Now, just one final thing to point out. I'm going to go right back to the very beginning and take a look at this reaction right here. Notice +2, +2, -1, -1. No Leo, no Gur. Precipitation reaction. Not all reactions involve a transfer of electrons. Remember, this was ion sticking to ion. All right, so good luck with your problems, and I'm going to get out of the basement.